This is Wayne Palatkin, and I'm going to go over how AlphaZero trains itself without any outside data. This video assumes you know what AlphaZero is. In short, it's a general-purpose version of AlphaGo Zero, which is an evolution of AlphaGo that can play board games like Go at the world champion level without needing any training data. The short answer is right up top. You record the MCTS policy array and put it in the model's loss function. You train the model to predict the winner of the given board state and reproduce the policy array. Of course, there's a bit more to it than that, and I think it's important to start with the concepts at the core of AlphaZero. The first thing to understand is that AlphaZero is not a monolithic end-to-end neural network that does everything. It's a tree search sampling algorithm combined with a neural network. Sampling means you're looking at a sample of the search space because there are just too many options to consider. AlphaZero uses Monte Carlo tree search, MCTS, to do this. Combined with the neural network model, MCTS does two critical jobs: policy improvement, which you can accurately think of as deep learning augmented tree search, and policy iteration, which is the inverse, tree search augmented deep learning. Policy improvement takes the model on a tour of multiple potential futures and builds the policy array, which is a ranking of which move to make next. Policy iteration is the self-training or self-play part, where the model is trained to reproduce the result of MCTS. This will be clearer if we take a look at AlphaZero's decision loop. First off, the output is an action recommendation. That's an argmax on the policy array. An argmax is an array's greatest value, or the index of its greatest value. MCTS builds this array by running a number of simulations. Now we're getting into the core of things. Each simulation is going to run a select eval backprop loop. The way that works is, for each simulation, MCTS will explore the search tree by selecting new nodes until it gets to either a game over state or an unexplored state, at which point it'll run the new state through the model to get its action value and action probabilities, and then trace its path back to the root node, adding the new value to the action value of each node along the way. It also keeps track of how many times it's visited a node. MCTS will do that for the number of simulations specified, and the result is a policy array consisting of the number of times each of the root node's potential actions were visited. The root node is the game's current state. Now is a good time to take a look at our selection equations. Every time MCTS gets to a node, it has to pick a potential action. It does that by running an argmax on an upper confidence bound array, UCB, which looks at the node's state S and actions A. UCB is a sum of Q and U. What are Q and U? Q is just WSA over NSA. W is the path action value. It's just a sum of the action value V of every node leading from this one. N is the number of visits of the node that action leads to. So Q is just the mean action value. It's an average of state values over visits. It prioritizes consistently high returns on investment. U is a little more complicated. It encodes exploration. It scales big PSA by cpuct and multiplies that by the square root of the sum of visits to all actions from the current node over 1 plus the visit to the node the action leads to. Note that each action leads to a node with a state, and each node tracks the number of times it's been visited. So take the root of the sum of that for all available actions and divide by 1 plus the visit count for the action you're considering. It's plus 1, so you don't divide by 0. So it's an inverse root normalized visit count. Basically, the fewer times the node's been visited compared to its siblings, the bigger the number will be. U is an exploration value. It prioritizes novelty, unexplored potential winners. cpuct is a constant MCTS exploration parameter, which is just set to 1 in the paper. Finally, there's big PSA. This is noise applied to the action probabilities, little p. It's 1 minus epsilon times the probability of this action, plus epsilon times eta for this action. Epsilon is set to 0.25, and eta is a Dirichlet distribution with the same length as the number of actions, where the alpha parameters are all set to 0.03. So big P is post-processed action probabilities. In the end, U is proportional to the processed action probabilities over visits. Note that Q only looks at state values, and U only looks at action probabilities. Now that we see how selections are made, let's go through an example. Here we have a partially explored search tree, and we're going to follow MCTS through one simulation. T is time step, S is state, V is state value, N is a node's visit count, and the A's are potential actions. We start off at the root node, that's the current state of play, having to make a choice. MCTS builds this UCB array and runs an argmax to pick an action. That gets us to a state one step into the future. This state exists and it isn't a game over, so we have to choose again from here. We increment the node's visit count, build an array, and pick the argmax. This time it chose action 0. Rinse, repeat, and finally we get to an empty node. Our path so far has been select after select, but now we're at an eval. To get the new state, we query the state engine with the previous state and action to get the next state and its list of valid actions. A state engine is the program that manages the game itself. You give it a game state and player move, and it returns the new state, list of valid moves, and tracks scoring. We then run that state through our model F, which returns little p, an array of action or move probabilities, and v, the state's value. We set the new node's visit count to 1, and now we're ready to backpropagate. Before we do, here's a very important note to understand AlphaZero. The model only answers 2 questions. How likely is a win from this state? And if I were the player whose turn it is at the state, how would I rank my available options? That's it. AlphaZero plays both sides. It has to do its job. Because of this, it has to look at state values and action probabilities from the relevant player's perspective. In effect, this means state values flip sign at alternating layers of the tree. Implementation-wise, this can also mean that the actions and value of a node are sign flipped because the state is from the previous player's perspective and the actions from the current player's. Adding positive and negative values lets AlphaZero consider long-term consequences by encoding any advantages the opposing player may get. For example, an action that gives the opposing player a big opportunity to score against the current player is going to have a lower value than if it didn't. AlphaZero tries to simulate the best move for a state's player at each time step. Note that for some games, historical context is important. In the case of Go, the last 8 board states, including the present, are passed into the network. So now that we've reached a new or end state in the tree, we backpropagate. We keep track of that final node's state value, and we retrace our path back to the root node, adding the final value onto each node along the way. When we get back to the root node, it's time to update the policy array. Once we're finished with our simulations, the policy array is just the number of times each of the root node's actions were explored. For context, in the papers, AlphaZero runs 1600 simulations and AlphaZero 800. We transform the policy array pi from an array of counts to an array of exponentiated visit counts to be our search probabilities. This is similar to the inverse of what we did with visit counts in the exploration value u. For every action, we exponentiate its visit count to 1 over tau and divide that by the sum of all visit counts to the 1 over tau. Tau is a temperature parameter that controls exploration. DeepMind set it to 1 for the first 30 moves and near 0 afterwards. The reason is policy selection is probabilistic, so setting tau to 1 just normalizes each count by the sum, which encourages some exploration early on when the tree is empty. But we do want AlphaZero to win, so after building the tree a bit, setting tau to near 0 turns the exponent into a very big number, leading to there being many orders of magnitude difference between policy values. Since selection is probabilistic, this is effectively an argmax. So this is a mathematical way of saying that after the first 30 turns, we choose an argmax with the slightest hint of randomness. And that chosen index is the action AlphaZero plays for the move. Note that since it uses a tree, there's only one way to get to each node, so each future is the result of a particular past. That means MCTS will never see the subtree stemming from the moves that aren't ultimately chosen. So to save memory, the subtrees of all sibling nodes are dropped every move. Any future can't be changed because its past has already happened. In simulation, that is. That was policy improvement. To get AlphaZero to train without outside data, we record the policy array pi used for each move, the associated state at time step t, and the winner of the game z from the perspective of the player at that time step. Recorded games become training data we uniformly sample from. We modify the loss function to include the policy, winner, and time step of a given state. The loss equals the squared difference between the winner z and the predicted value v minus the MCT search probability pi at that time step times the log of action probabilities p plus L2 regularization. C here weights L2 regularization, and theta represents the model's parameters, also called weights. V and P are the output of the model given a state. The rest is deep learning. You train on many batches of data to reduce the loss. Now, since the model is a party to creating the dataset, what we have is a dataset representing a kind of player. If you want multiple instances of AlphaZero at different skill levels, you can just save a copy of the model after training on a set of games. That's policy iteration. As you can see, AlphaZero is a very tight integration between a model, tree search, and state engine. The state engine provides a signal of ground truth that guides AlphaZero when the model is randomly initialized and unable to interpret a state. MCTS takes the model on a tour through potential futures and encodes what's effectively a differential equation multiple time steps forward. The model focuses on perception, judging how likely a state is to lead to a win and predicting move probabilities, essentially single label classification. One of the things that makes AlphaZero such a powerful algorithm is that it doesn't over-rely on the model. Instead, it lets it focus on what it does well and incorporates it into a larger machine as a tunable subprocess. And that's an overview of how AlphaZero works and how it's able to train without a dataset. It pretty much creates its own. There are more details when it comes to actually building it, but hopefully this gives you some context to help understand what's going on in the papers and the few code implementations that are out there. All right then. Thanks for listening.